Today we are going to be discussing a very important topic in supply chain management, matching demand with supply. And that is the overall goal of supply chain management. But we're going to, for this goal, we are going to look at a strategy called accurate response. A version of this strategy is also called quick response, QR. You might have heard of quick response, and accurate response is another term for that. And within the discussion for accurate response, we're going to discuss what is the role of forecasting, what is the role of postponement, what is the role of reactive capacity. Accurate response is the idea that even in uncertain environments, you can do a pretty good job of matching demand with supply. And we're also going to talk about how do you measure how well you are doing and so on and so forth. So it's a very important lecture. A lot of the examples will be from the fashion clothing industry or seasonal clothing industry where the selling season is short. You can think about winter jackets. Usually you don't want to sell winter jackets in summer because you can generate more revenue from other products from the retail space. You don't want to put jackets on your retail shelves in summer because they're not going to sell well. And so you wouldn't do that. So jackets really sell in a certain time period, right? Clothing is like that. Clothing is related to seasons, right? You have summer clothing, your fall clothing, because depending on the weather, the temperature, the type of clothes people wear will vary. And so because the original work on this strategy was done for seasonal clothing, a lot of the classic examples come from that, and some of the examples you'll see will be from that. But the ideas and the principles can apply to a wide range of industries. So let's get into this. Okay, so we want to understand the role of forecasting, as I mentioned previously. We'll talk a little bit about different types of forecast information used, and then we'll get into reactive capacity, matching demand with supply, and how best to use reactive capacity in accurate response systems. You can think of the lecture as having two parts. The first part will focus mostly on forecasting because the accurate response depends so much on forecasting and forecast error estimation. So you have to have some idea of that. Even if it's review, we need to go over that. And then you'll be ready and primed to really understand how the accurate response system work. So let's start with forecasting. These are a few quotes I found online. I'm not sure if Albert Einstein actually said the third quote on the slide because sometimes online things become popular that are not accurate. But the idea of that quote we're going to talk about. Okay. The first quote is telling us that you're going to make mistakes in forecasting. We don't know the future. It's very hard to predict the future. So the reason I put this quote is that if you're a supply chain person and your job is to do forecasting in the organization, it's important to set reasonable expectations. Okay, sometimes people who don't know much about forecasting things, if you just use cool algorithms or a lot of computation, or you throw some statistics at the problem, you should be able to get a good forecast. I've personally talked to managers who think that the biggest problem with their supply chain is they don't have accurate forecasts. And that is like a cop-out because sometimes very accurate forecasts are just not possible. That's the nature of the demand. It's very hard to guess the precise demand ahead of time. Even within the same industry, sometimes some products are easy to forecast, others are not. I remember that in the furniture industry where I worked at, some products like sofas and chairs were highly color dependent. So for the same sofa, a particular color may sell very well and another color may just totally not sell. And these products were difficult to forecast at the SKU level, where you have to specify a color. You have to tell the supplier, which color's chair to make, or the fabric on the chair, things like that. And we'll talk about postponement, where sometimes you can delay the step, where you add a feature to a product that really adds variability to the forecast or makes it hard to predict sales, like the color of the fabric. You want to do it at the end. You want to have the chair ready, and when you get the customer order or close to that, you choose the fabric. But in any case, furniture with fabric was difficult to forecast at the SKU level, where you have to know the color of the fabric. But other furniture like beds, side tables were much more easier to forecast. The forecast area was smaller because there were only 2 or 3 colors in each, and people, had less choice. They didn't have to pick a fabric, and some sets were popular, some were not, but they were relatively easy to forecast the sales compared to furniture with different colors available for the fabric. So you have to set expectations, right? Correctly. You don't have a crystal ball. You don't know the future. If you do have to forecast, you want to update the forecast often. That's the second code, because you want to incorporate the latest information you have. If you are seeing certain trends based on what the competitor is selling, or certain things are becoming popular on social media, you may want to update your forecast based on that new information. And then the last quote is asking us to think about, why are we forecasting in the first place? So I never think of the future. It comes soon enough. It's like forecasting is asking you to guess the answer when we will know the right answer eventually anyway. So why guess? Why not just wait until we figure out the right answer? Once we see the actual demand, the customer is in our shop and asking for a certain product, right? And the issue are lead times. The customer goes to a dealership, says they want a particular car, and if at that point GM decides to start production of the car and maybe purchase the tires and the transmission and the steel and the aluminum and the plastic, and then they put them in different molds and make the different parts and assemble the whole car and then give it to the customer may have to wait months for their car. And in many situations, customers are not willing to wait. So the lead time to produce something is a lot longer than the customer's willingness to wait. Whenever you have the situation where lead times are longer than customer willingness to wait, you have to forecast, because you have to produce in advance. Okay, so let's look at a few principles to keep in mind when we are thinking about forecasting. So the first one is, forecasts are always more accurate at the aggregate level, or the top level versus the SKU level. So what are some of the levels? The top most aggregate level you might think of as the GDP of the country you're operating in, right? Because that's the GDP is the sum of all the sales that happen in the country. Then below that level, it may be the sales of your industry, whichever industry you're in. And then below that level, it may be the total sales of your company for the whole year. Within your company sales, there may be different divisions or departments. So there may be, maybe you are a retailer that sells clothes and shoes and furniture. So maybe you have the sales of, clothing, and then you have the sales of footwear, and then you have the sales of furniture. So that could be departmental sales within the company sales. Then within each department, you may have categories, okay? Men's tops, women's tops, pants, and so forth. So then you'll have sales of each category. Then within a category, you may have subcategories and then sub-subcategories, and then eventually you have an item. An item could be, let's say, a polo shirt of a particular material, maybe, I don't know, some cotton polo shirt or something. Then within the polo shirt, you may have different colors. You may be offering that shirt in 5 or 6 colors. And within the color, you may have sizes. Okay. So the SKU, SKU is a term for stock keeping unit. It refers to the thing that the customer actually buys. So a customer does not buy men's tops. Customer does not buy a generic or a random polo shirt. They buy a specific size, a specific color of a specific item. So all of these specifics together, so the polo shirt in green color, size large, that is your SKU. Okay. And that's the lowest unit, the lowest level. You may need to forecast that. So that's the lowest level, and the highest level in practically for business would be your company sales. But if you're an economist, it could be the country's GDP, right? If you look at economist estimates for the country's GDP, the error is very small in percentage terms. They're off by 1 or 2%, or maybe a few percent. If you look at company sales, they can often be forecasted with an error of 5 to 10 or maybe 15%. So, if a company sales are, and you can look at financial analysts' projections for companies. If you follow stocks of certain companies, before the companies release their income statement or financial statements, analysts are projecting, oh, we think they're going to have this much sales. A very popular projection that analysts have been doing over the last few years, because Tesla's stock price is so volatile, has been how many cars will Tesla sell or deliver to customers each quarter. And every quarter before Tesla's financial statement comes out, all these analysts are posting their numbers, and then they talk about, oh, did the company beat our expectations or not beat our expectations? And you'll see at the company level, these analysts are often within 10% of the actual numbers. Even if a company beats expectations or fails to beat expectations, it's often within 5 to 20% of the analyst projections. So company level sales are not that hard to forecast, plus minus 10%. Usually, right? There can be exceptions. And then when you go below the company to the category or department level, then you go below to the item level, the forecast error tends to increase. Yeah. So why do we need to understand that? You need to understand that because let's say you have a forecasting team and they make a forecast of all the jackets you plan to sell in winter. When you add up their forecasts of individual jackets, so jacket 1 will sell this much, jacket 2 will sell this much, jacket 3 will sell this much, and you go through the list and you total up the forecast. And you get a total that you're going to sell 500,000 jackets. If you look at the category of jackets and you have historical data on the category, because maybe you've been selling jackets for the past 10 years, not the same jackets, but jackets in general. So if you look at the category of jackets, you may realize that you've never sold 500,000 jackets in a year. Last year, maybe you sold 230,000, and maybe you project this year to grow by 10%, and maybe you're gonna sell, 250,000 and some change jackets this year. That's your category level projection based on historical data, maybe some other factors like GDP of the country, inflation estimates, things like that, unemployment estimates. Maybe with that you build a model and you project that you're going to sell about 250,000 jackets. But the individual jackets forecast, you're adding up to 500,000. That's huge. That's way more than the category level forecast. So who is wrong? It's highly likely that your individual jacket level sales are inflated. Especially sometimes salespeople or product managers get excited. They like each and every single jacket. Otherwise, they won't be selling it, right? So for the company's employees, if they're selling, 100 different types of jackets, maybe they like all those different models of jackets and colors and so forth. And they get excited and they say, oh, this is going to sell well, this is going to sell well. But the total is unreasonable. So then you would trust the category level forecast more. You say, okay, I'm reasonably certain we're going to sell 250,000 jackets, maybe plus minus 20%. You guys are forecasting a total of 500,000. That's unreasonable. So you're going to reduce your individual item level forecast or SKU level forecast until they sum to 250,000, or maybe you give them some leeway. Maybe they sum to 270,000 because maybe we'll sell 270,000, but there's no way we're selling 500,000 jackets. So knowing that the higher level forecasts are more accurate gives you a sense check on item level forecast or SKU level forecast. Without this sense check, your item or SKU level forecast can be too extreme. The second thing to know is forecasting is more accurate for the near term than the long term because, the forecasting you're forecasting, in the end, you're forecasting human behavior, because humans have to make purchase decisions to buy your product. And it's easier to predict in the short term because fewer things will change, right? Between today and the next month, the economy of the country is probably going to look the same. The unemployment rate is probably not going to move too much, right? And purchasing powers are not going to change drastically over a period of a few weeks in the country. And so decisions of your customers are probably not going to change drastically either. So maybe I can forecast what's going to happen next month in terms of my sales relatively well. But if you ask me about next year, who knows what's going to happen by next year? Maybe there's an election, the government changes, the policies change, maybe a new war starts, maybe a war ends, maybe something else happens, right? More things can happen that affect the behavior of consumers. If you tell me to look at 5 or 10 years, all bets are off, right? Anything could happen in that long time. So that is why we forecast for the short term, and then we update our forecast often, because if I forecast for 2 months out, then as I get closer to that time period, maybe I can incorporate new information and revise the forecast and update it. But short-term forecasts are more reliable than long-term forecasts. Practical significance of that is, if you are able to reduce lead times in your supply chain, your forecasting almost automatically becomes more accurate, because before you had to forecast, let's say 4 months out, because your lead time was 4 months and you need to produce 4 months in advance for the next 4 months of demand. And now suddenly your lead times are 1 month only, and now you only have to forecast for 1 month out at the item level. Maybe you can forecast at the category level for a whole year. So you tell your suppliers, I'm going to give you orders of jackets for the next year about this much. You can buy raw materials or whatnot. But the actual item level orders, okay, send me this jacket, this color to this warehouse. Maybe you need to place only for 1 month in advance, because lead time is now 1 month. So when your lead time shrinks, your forecasting horizon shrinks, and shorter horizon forecasts are more accurate than longer horizon forecasts. Some products are inherently more forecastable than others. What do I mean by forecastable? That means their forecast error is less. So, within your business, if you sell many different items or services or products, you realize some items are inherently more risky. Sometimes they're more expensive with high margins, which is why you have them, but they're hard to predict the sales for. And that's important to know. You need to know for each item, what is the risk when you order the item or decide to produce it, right? Because if the forecast is highly unreliable, the risk can be more versus an item with a more reliable forecast. So knowing the risk you're taking when you produce an item in advance or order it in advance is useful, and you'll see how that's useful later in this lecture. Okay, so let's talk a little bit about how, and we're not going to go into the nitty-gritties and the mathematics today. We're just going to look at overall, so you understand the overall forecasting process. What sort of information is used to build statistical forecasts? Now, remember I said higher level forecasts are more accurate than lower level forecasts. The higher the level, often you have a lot of historical data as well. So for your company's sales, if your company's been around for 10 plus years, maybe that's just been around for 100 years, you have 100 years of company sales data. You may not use 100 years of company sales data. You might say 100 years ago, the world was very different. That data is no longer relevant. I'm only going to use the last 10 years of data, which is fine. But still, you have 10 years of data or 20 years of data or 15 years of data. So you have data you can run statistical algorithms on, and time series analysis and so on. For item level forecasts, sometimes you do have 10 years of data because you've been selling this product forever. But often, especially in fashion industry or clothing industry, you might be launching new products or new design styles all the time. So maybe for half of your items, you have maybe 5 years of historical data or 10 years of historical data. But for half of your items, you have only 1 year of historical data or no historical data because they're new items for this year. So when you have no historical data or very small amount of historical data, you cannot really do statistical forecasting, right? Because statistical forecasting requires historical data or data on variables that affect the forecast. So what variables lead to demand of your products, and that's also usually hard to get. So often statistical forecasts are done at higher levels, company level, department level, category level, maybe subcategory level. At these levels, you'll use statistical methods to do forecasting. And then when you get to the item level, if there is data for certain items, you can use statistical methods as one of the methods. And then you'll often adjust them based on judgment, or you just look at the small amount of data you have, 1 or 2 years or 1 or 2 quarters. And based on knowledge of what competitors are doing, what's happening in the market, you'll do a judgment forecast, which is just based on a little bit of data, but it's not a statistical forecast. Okay, so historical demand data is basically just past data. What did I sell of this category, this subcategory last month, last 12 months, last few years? Okay, and the statistical analysis of this historical data usually looks for correlations. Okay, maybe the sales in September are always related to last year's September sales. So there's some seasonality. Back to school happens in September, and you sell items like school uniform, and their sales picks up in August and September. So that's a correlation in time. Okay, this August sales and September sales are related to last August and September sales. So these correlations in time, statistical methods are really good at finding and exploiting these time-based correlations. You can deal with the trend and seasonality. So seasonality is when certain seasons or months your sales go up or down, like ice cream sales go up in summer, that's seasonality. So statistical methods are very good at dealing with seasonality and a trend. If they see like a short-term trend, okay, last couple of years your sales is going up, most likely going to go up this year. And so they can deal with these sorts of things very nicely. You can also have statistical models that give more weight to recent data than really old data. And the assumption of all of these time series models is that some part of the history is going to repeat itself. So in your historical data, there's signal and noise. Noise is just idiosyncratic events that just happen once and are not going to repeat. And signal is what intends to repeat, those parts of consumer trends or consumer behavior that you expect to repeat. That's the signal part of your data. And so you use statistical algorithms to average out the noise and kind of project the signal in the future. So you have ARIMA models, ARIMA X models, seasonal ARIMA models, time series decomposition models, these sorts of time series analysis models that can do this job for you. Then you have indicators of sales. So the price, often we know the price we're going to sell a product at ahead of time. So if I'm going to sell a particular jacket in the store, the marketing team would have a plan. Oh, we are going to price this jacket at a certain price, right? So we already know the price. And if a lot of our items are price sensitive, where people buy more if the price is low and so on, then price becomes an important factor to consider in our forecasting. It's surprising, it's such an obvious factor that in real life, so many managers build their forecast without systematically including price as a variable in a statistical sense. So they'll say, oh, I know I'm going on discount next year, so I'm just going to inflate the sales by some hand-wavy fashion. But to have a statistical analysis of, what price change leads to what sort of effect and incorporate that in your forecast, all this very easy to do with the methods we have. A lot of people don't do it, which is unfortunate. So price is an important variable you might want to consider. Other variables could be you have, let's say you sell large ticket items like appliances. Sales of large ticket items tend to be correlated to the GDP of a country, or employment, average salary in the country, a low employment in the country. So if people have jobs and they're earning a lot of money, they tend to buy more of the big ticket items. So if you sell big ticket items, you might say, oh, for the next quarter, I have a GDP forecast from Economist. I have an unemployment level forecast from Economist. These are pretty accurate forecasts, so I can use these. And I also have this data for the past. I know for last year what was the expected GDP or the actual GDP. And so you can incorporate these variables like GDP growth or GDP, unemployment levels, into your category level or company sales forecasts. Then in some industries, you have early signals, which call leading signals. Leading signals are data points that you can observe today and that tell you something about the future. Okay. A very important example is construction permits. So when construction permits are given out, after some time of getting the construction permit, construction starts. And when construction starts, that project needs to buy wood, lumber, steel, concrete. And then if it's a building, they might need to buy lights inside, wiring. All sorts of products go into construction and building. Many industries are linked to construction and building. So if you can get data on construction permits, for example, and if construction permits have gone up, you know that most likely your sales of products related to construction might go up as well. There could be scheduled events. Maybe you sell t-shirts with for certain bands of music or certain types of t-shirt which are popular with music people who like to go to music concerts. And if in your state or city a band is going to be visiting for the next 2 months or the next month, you might say, oh well, probably my sales are going to go up that month because these items will be in demand, right? So you might have a variable, and this may have happened in the past. You may have historical data where you have marked the weeks or the months where a concert happened. And so this variable is 0, 1 variable. It's 1 when that time period there was a concert. It's 0 otherwise. You can incorporate that into your statistical forecasting. And for future, when there is a concert scheduled, you make that variable 1. And the forecasting model says, okay, for that future, where the variable is 1, this is the projected sales. If the variable was 0, the projected sales would fall. Okay. And then the last thing you want to know about these statistical models is that, and there are competitions where a lot of time series are given to people, and they use different forecasting models to try to estimate the future values of those time series. In these competitions, what has been learned is that almost always combining the forecast from different methods produces a more accurate forecast than just using one method, which is kind of counterintuitive because you would think, okay, one method is going to be the most suitable and the most accurate. So if you have a method that seems to work best in that situation, why would combining the forecast from methods which don't work as well improve the forecast? And the reason is that you may combine them less accurate methods, you may give them less weight, but you still want to combine them because these other methods, they may capture parts of the signal that your method ignored. But giving them a smaller weight but still including them, you include some of that signal that your best method missed in your forecast. So in statistical software, you can run like 4 or 5 different forecasting methods and then do a weighted average of the forecast from those 4 or 5 different methods, and that'll be your final forecast. Okay. Now, there may be information, we kind of talked about this non-numeric information. For example, a competitor opened up shop next to you or entered your state or left your state. And these changes in the market can really affect your sales and the forecast. There could be expected tariffs, things like that. A lot of times if an event is repetitive, so for example, it's like I gave you the example of a music concert. So, in a large city or a particular state, you may have bands visiting very often, multiple times a year. So every year you have certain weeks or months where there's a concert. Okay. And so when events repeat, similar events repeat, you want to factor them into your statistical model using variables, 1-0 variables or other types of variables. But if it's an event that doesn't repeat every year, doesn't happen every year, so change in tariffs may happen once in 10 years, change in the marketplace, new competitor, which is a serious competitor entering or exiting, may happen once in 5 years or something, then these types of features you may want to adjust your statistical forecast for these features that as a manager, but the statistical forecasting software does not have data on them because these are rare events. They don't happen all the time, so you don't have a lot of data on them. Okay. So we are pretty much, so before we proceed, we're looking at a little bit about how do we use forecasting software and forecasting error. It's a very important point. Think about the bottom half of the slide, the food for thought. Let's say you're trying to build a forecasting model, you're testing different things, and you realize, sometimes you go on promotion, you give discounts, you run a promotion, and you may see that, your sales tends to have the same level or the same trend. Nothing really changes much when you're on promotion and not on promotion. And so you might decide, I'm giving these discounts to the customer. Customers are not buying more quantity. My revenue is price times quantity. So if I sell something for $10 and sell 100 units, I make $1,000, 10 times 100. I gave a discount, I'm selling it for $8, I'm still selling 100 units only. Quantity did not go up, price went down. 8 times 100 is 800. So my revenue went down from 1,000 to 800. Why am I giving these discounts? Discounts and promotions make sense if the quantity sold goes up. If the quantity sold is not going up, why am I giving these discounts? This is not really forecasting, but it's such a related area. Companies often want to evaluate the benefit of the promotions. I ran a promotion, what's the benefit I got? How much more profit or sales I made from running this promotion? And sometimes it can be tricky where data seems to show there's no benefit of promotion. Your quantity did not go up. Okay. Let's say this company says, we are a data-driven company. Doesn't make sense to run a promotion if our sales are not going to go up. So let's stop running promotions. They do that and their sales actually decline. Promotions were actually keeping the sales steady, otherwise they would have declined. What could have happened? Sometimes what happens is that your competitor is going on promotion and your product is so similar that if you don't go on promotion, people will switch to the competitor. Think about Pepsi and Coke. You'll often see Pepsi and Coke go on sale at the same time. Why? Because if the consumers think, well, maybe some people have very strong choice, but a lot of consumers might think, well, if Pepsi is cheaper today than Coke, why don't I just buy Pepsi? It's about the same for me. And they switch. Then if Coke runs a or Pepsi runs a promotion and Coke does not, Coke sales might decline, right? So when you have substitutable products and your competitor runs a promotion, sometimes you have to match. Even though by matching your sales don't go up, but they also did not go down. You prevented a sales decline by matching the competitor's promotion. So we have to be careful in forecasting. When forecasting says, oh, this variable is not useful, so we can throw the variable out, that variable may not be useful. But to say that promotions have no effect, you want to be very careful how you estimate that and how do you come to a conclusion about whether they're useful or not useful. I mean, you can still do it. You can look at competitor sales. You can model the switching behavior. All of that can be done. I'm just saying a simple analysis may not reveal that, so be careful. Okay. For statistical forecasting, people will often use statistical forecasting software. SAS has stuff built in. If you use SAP, sorry, not SAS. SAP, the ERP software many companies use, has forecasting built in. I believe most enterprise resource planning software would have some forecasting tools built in. A lot of people will use those tools. When you do use forecasting software, you want to figure out, okay, what's the forecasting error? Okay, how accurate are my forecasts? You can look at error statistics like mean squared error or mean absolute deviation, which is the average error. So if MAD is 100, on average you're 100 units off. Mean absolute percentage error, this is a percentage. So if it's MAPE is 10%, you're off by 10%. MAPE is very useful because you can compare products with with different levels of demand. So you can say, oh, this product, the MAPE is 10%, this is 20%. You can compare across categories. If you don't use MAPE, you use something like MSE or MAD. what can happen is that the highest selling categories also have large errors. If you sell 1,000,000 units of something, the error may be in the tens of thousands. And if you sell 100 units of something, the error may be in tens. So the magnitude of the error is related to and relative to the magnitude of sales of that item or category. And so percentage just makes them all a percentage. So you can compare, oh, here error is 10%, here error is 10%. And so that's useful to compare across categories, across products. Bias is if you're forecasting is consistently up or down from the real demand. So maybe you're consistently forecasting too high, or you're consistently forecasting too low. How high on average you are, how low on average you are, that'll be the bias. You want to have a bias of 0. You should not be forecasting too much or too low. You should be trying to hit on average the target on the head. So you want bias to be close to 0. With newer forecasting techniques, especially machine learning algorithms, or even with time series algorithms, sometimes you want to have a holdout sample. And so you train your algorithm, or you estimate your model, let's say for 80% of the data, then you apply this model to the next 20% of the data that was kept separate, called the holdout sample, and then you measure the accuracy of your model on the holdout sample. That can often give you a better estimate of how accurate your forecast will be, because when you fit a model to the data, the model can overfit the data and try to do a really good job for this particular data that you have. But outside this data, for new data, its performance may be very poor. So that's what overfitting is. You overfit to the noise, not just the signal. And then when you project forward or you predict the future, you're way off because the noise is not projectable in the future. The noise was idiosyncratic events. You want to project the signal forward. And so holdout sample prevents against overfitting to the noise. And so that's often a useful technique to use with your forecasting software, to use a holdout sample to make sure you have an idea of how accurate your forecast is really going to be. You need to understand what factors and variables were considered by the software. Did it consider seasons or not? Did it not consider seasons? Did it consider the competitive landscape, if that is changing or not consider it? Sometimes there will be factors the forecasting software did not consider, such as a new change in regulation coming up, or change in customer taste that just happened, maybe because of COVID or some external event, things like that. And then you may have to adjust the forecast. So imagine COVID just started, lockdown started happening, and your forecasting software does not have COVID and lockdowns in its history. So it's still going to project a high demand, but you as a manager know, oh, lockdowns are happening, I'm not going to sell that much. And so you have to make manual adjustments. So often people will start with the forecasting software, but then also make judgment-based or manual adjustments to the output of, or the forecast that you get from that. Okay, so we talked about at the higher level, company level, category level, subcategory level, you can use statistical methods to forecast because you have historical data. But what about for items and SKUs, like a particular shoe? Maybe it's a new design of a shoe. You don't have any historical data. So how are you going to forecast that? And for that, we often use team-based judgment forecasting. Usually you want more than one person to do the forecast. One person can have their own biases. They may not have all the information or knowledge necessary to make a good forecast. So often you set a team, and the team, they come up with their individual forecast, and you combine them in some way to build the forecast. So this may be a good time to take a short break. If you're watching this lecture in one go, you could pause the video, get up, stretch, have a cup of coffee, and come back. This is, going to be about an hour and a half type of lecture. So I would suggest watch it in 30-minute chunks, take some breaks during it. Team-based judgment forecasting. Okay, so this is used when software-based forecasting approach is not accurate at the desired level. You're doing low-level forecasting of items, SKUs, individual items, SKUs. They don't have a lot of historical data. Sometimes they do. Maybe you sell fuel at a gas station, and the fuel you sell at the gas station has not changed for the past 2 decades. And you can have 2 decades of historical data. So it's not always that you don't have data at the SK level. But this lecture is about accurate response. And accurate response is used used when things are hard to forecast because they change a lot or because there's new items, like in the fashion industry, clothing industry, and so on. So in the context of accurate response, you're not going to be able to have a lot of historical data at the SKU level usually. And so you may not be able to use software-based statistical forecasting at the SKU level. You'll have a category level forecast from the software, but now you need to get the item level forecast and you have to do something. So in such a case, sometimes, one way is to use judgment forecasting. Okay. Or the other option is, let's say you have some historical data, you run a forecasting model, but it's not going to be very accurate because things are changing and it's not incorporating all of these changes because they were not part of the historical data. And then you start off with a statistical forecast, but you're going to update it based on judgment forecasting. So often we'll use a team. Team tends to do better than one person. You can have sales staff, marketing staff, store managers, which deal with customers, regional managers, data people who may be able to tell you how the category works at the data, using data at the category level, and that may have some insights for the items. So you put this team together, and then they're going to come up with their forecast. You'll see this happen if you play the Global Supply Chain Management Simulation game by Harvard Business Publishing. That game may be part of your project for the course or an assignment in the course. So if that is, you'll see a team coming up with a forecast and the forecast will not agree and you'll have to decide what to do. And so, in team-based forecasting, you can force a consensus, tell the team you have to come up with one number for the whole team, or take an average of the different forecasts that each member comes up with. Okay, so mean forecasts have a lot of advantages, and we often use these for accurate response. And because when you have different forecasts of different people for the same item, the variability or the differences in these forecasts give you important information. Let's say you have a team of 7 experts or 7, sales staff, store managers, all these people who are relevant to the item and then understand the customer and understand the market. Let's say these 7, each one makes their own forecast. So you get 7 different forecasts. If all 7 forecasts are very close to each other, then often this forecast will be quite accurate because 7 different people coming to the same answer by applying their individual knowledge. That means the answer is kind of obvious or forecastable, and they were able to forecast it. Okay. So that's the third point. Variation between individual forecasts often predicts how accurate the final forecast will be. If they all disagree, one person says you're going to sell a very high amount and another person says you're going to sell a very low amount, then the forecast, the actual sales may be far from the forecast. You can't trust the forecast as much. The forecast error will be larger because your team of experts is not agreeing with each other. They have a lot of disparity, so that means it's hard to predict. Hard to predict items will have more disparity. People will go with different gut feel or whatever they think. Forecastable, predictable items will tend to have less variability between the judges or the forecasting team members. Yeah. So that's very useful because if you know certain items that have high forecast error, you can plan for that. You can have safety stock or you can use reactive capacity. We'll look at those things later on. Okay. Also, the other advantage of using the average forecast is that you may have a dominant person in the group. If everybody has to give their own forecasting number, the dominant person can't influence the number of other people as much because, everybody has to give their own forecast to you and then you might take the average. In a consensus-based forecasting where the team has to come up with one number, dominant personalities will tend to dominate. So somebody could be very knowledgeable or very good at forecasting for certain items, but they may have a quiet personality. They don't speak up as much. They don't speak, very forcefully. And so their views may not be represented much in the consensus forecast. So that's a problem. If the team says, we have to give our own forecast, so they don't really debate each other much, there could be reduced sharing of information with each other because, if the forecasts disagree, they don't have to come to an agreement. They just give their own forecasts. And so they're not forced to explain to each other why they think their forecast is right and your forecast is wrong, and so forth. Okay. In consensus-based forecasting, the advantage is that team members, the process of coming to a consensus number forces them to learn from each other, learn the assumptions of each other, and then sometimes a member can say, oh, I didn't think about that. That is why you moved your forecast up or down. I agree with you. I'm going to move my forecast up or down, or agree with your forecast. So this learning or information sharing can happen better. I mean, there are other ways to do it with team-based forecasting as well. You can have people list out or document all the information or feelings or opinions they have to which they're going to build their forecast on, and then you can share this document around the team so everybody reads everybody else's opinions. So there are ways to get around it, but in general, in a consensus-based forecasting, people learn from each other more. The biggest disadvantage is loss of information, because when you come up with one number as a team, you lose the information about whether the individual forecasts were agreeing or not, and that's important information, because as I mentioned, when different forecasters agree, they tend to be accurate, and when they disagree, there tends to be more risk or more error in the forecast, and that's important information to have. So can we come up with a better way that combines the strengths of both? As I've already hinted, yes, we can. You can pause the video, think for a few minutes, and then replay the video and see my thoughts on it. So I think you can. I mean, you can have a mechanism which is more formalized, where let's say every member starts with an individual forecast, and they also document the reasons. And then that document with their forecast and the reasons for the forecast is passed around. So everybody gets, other people's forecast and the reasons. They read other people's forecast and the reasons, and they think, okay, do I need to revise my forecast? Because maybe I've learned new information from other people. If they do, they revise their forecast and write the new reasons. Okay, I revised my forecast for this and this reason. And again, you do a second round. And after a few rounds, you'll see that the forecasts don't move much. Even though people have got all the information from other people, they've come to their final answer. They think their answer is now correct, even if they agree or disagree. And then you can use that, calculate the mean as the average forecast, look at the differences between them to look at the variability or the estimate, the forecast error that way. So it's a way, sometimes it's called the Delphi method, which is used for long-term forecasting, where experts write their forecast and write the reasons, and they share that document with other experts, and then other experts reply and respond, and then they update their forecast. So this whole method is very long, which is why it's often used for important things or strategic things. Let's say you're launching a new product. I said before the iPad existed, Apple wants to launch a tablet now, and there's not many tablets out in the industry. And so you might do that to have experts who use experts on laptops and smartphones and other experts, and they're trying to forecast whether the tablet will sell a lot or not. And so you can do that, because that's a big strategic decision. But if you have hundreds of SKUs and you try this Delphi method on all of the SKUs, it's going to take you forever to finish forecasting. So often you don't have enough time to do this method at the item or SKU level. You might do it for strategic decisions, for new strategic directions for the country, for new products you're launching. But for all SKUs, it's usually too costly and time consuming to do this. Okay, let's look at some issues that can happen with forecasts and using forecasts. So first up, you need to understand the difference between demand and sales. Okay. When you have sufficient inventory, and we're talking about products that are sold from as a finished good, so the product is produced and stocked, and then people go to the shop or online and buy the product. It's not customized to order. Some products you place the order, then the product's custom manufactured according to your specifications, and then they give it to you, right? So let's say you want to build a custom house. So you go to a builder, you give your custom order, and then the builder builds the house. So in that case, demand equals sales, because there's no lost sales happening. But when you're selling from inventory, already finished goods inventory, then if you never run out of inventory, then whatever demand was, you fulfill the demand, so demand equals sales. But if you do run out of inventory, then the demand that happens when you're out of inventory, you're losing that demand. People are coming to buy the stuff and they're not finding the inventory, they're walking away. Imagine you have empty shelves of a particular item in retail stores. For some of the days in a week, the weekly sales for that week will be less than demand, because when you had 0 items in stock, some people went to buy those items, they didn't find them in stock, and they went to a competitor, they went away and bought something else. And so you will have some sales when you had non-zero inventory, but your sales are not equal to demand. Demand was higher, but you missed some of the demand because you ran you're out of stock. You had 0 inventory. Okay. Now, let me explain the second point here with respect to a figure. So, forecasting methods try to be unbiased. So they are trying to forecast the middle of this distribution. So if the demand for future is random, like it's not known with certainty, it could be any value between the minimum and the maximum value. We're trying to hit the middle peak. We say, okay, on average, this is what the demand is going to be in the next time period. So there's a 50% chance the actual demand will be higher than our forecast, and a 50% chance that the actual demand will be less than the forecast. So if you produce quantity equal to the forecast, there's a 50% chance you may run out of stock because demand is more than the forecast, and a 50% chance you may not run out of stock. And so if 50% chance of being out of stock is too much, you may produce more than the forecast. And how do we know that? We can look at what we call cost of excess versus cost of shortage. Okay, so we compare the benefit of selling an additional unit to the cost of having an extra unit. Okay, so let's say you are going to order 100 units. If demand is 101, what did you miss out on? You did not sell 1 extra unit you could have sold had you ordered 101. And so the profit from this extra unit you lost. So let's say you make $10 of money on every unit you sell. So if you made 100 units, demand was 101, you lost the $10 of profit. On the other hand, let's say you produced 100 units and demand was 99. So you sold 99, you're left over with 1. Now you have to get rid of it, sell it for a discount, or hold it in stock for a long time. All of that is costly. So that costs you $5. And maybe you have to give a discount or something. So that's the cost of an excess. You had too much inventory, 1 extra inventory piece, and that cost you $5. The other one is the cost of a shortage. You had 1 less unit, so you lost $10 of profit. So the cost of shortage is the benefit from a sale, and the cost of excess is the cost of holding inventory or having to get rid of the item on a discount and so forth. So we compare this cost of excess and cost of shortage. The benefit is the cost of a shortage is the benefit you get from sales, because that's the benefit you lose when you have a shortage. And the cost is the cost of excess. That's the cost of inventory or having extra items in stock. And so if your benefit is a lot more than the cost, which means the benefit of selling an extra unit versus the cost of keeping an extra unit, if this benefit is more than the cost, you might produce more than the forecasted quantity because you want to have a higher chance to meet all of the demand if the demand is higher than forecast. And same thing vice versa. If there's very little margin, you don't make a lot of money by selling extra items. But if you have extra items left over, like unsold items, then they expire. Maybe they're like eggs that go bad, so you lose a lot of money. So in that case, you might even decide to produce or order from your supplier a quantity less than the forecast. So you can adjust the forecast quantity up or down, looking at the normal distribution. And the standard deviation of this normal distribution depends on your forecasting error, because the more accurate the forecast, the more thinner this distribution will be. The less the forecast accuracy, the fatter the distribution will be. Okay? And so you may adjust the quantity you actually produce or order from the supplier up or down from the forecast, depending on the cost of excess versus cost of shortage, or in other words, the benefit from an additional sale versus the cost of carrying an additional item. that benefit versus cost calculation will push you either to order more or less than the forecasted quantity. Okay, so you want to understand the difference between demand and sales. That's number one. So if you ran out of inventory for those time periods where your inventory was 0, you're not measuring demand. So oftentimes people will they will interpolate sales data, interpolate the data for time periods where inventory was 0 and hence their sales was 0. If you do have inventory and your sales is 0, that's not a problem. That means demand was 0 during that time. You had inventory to sell, but nobody came to buy it. But if your sales is 0 and inventory was 0, then that means that 0 is not a true 0. Probably you had some demand, but people couldn't buy it because you didn't have any inventory to sell. So there maybe you don't want to put the zeros into the forecasting software. You want to replace those zeros by the average demand in that time period or something like that. Interpolate the values because you did not measure the true demand. You had lost sales. You lost some sale. The other thing to understand is based on the benefit versus cost calculation, you may decide to produce or order a quantity larger or smaller than the forecasted value. Okay. So that's it for forecasting. We talked about, statistical forecasting. We talked about judgment, team-based forecasting. We talked about how to use the forecast, how to understand that, when you have lost sales, or your sales data is not capturing the entire demand. These are all important topics that help you understand why we do certain things in accurate response.